Suzanne went to the bank and withdrew $800. The teller gave her this amount using $20 bills, 50 and 100. With at least one of each denomination, how many different collections of bills could Suzanne have received? Well, the 800 would have to be 20 times something plus 50 times something plus 100 times something, and X, Y, and Z representing how many of each bill she has. So let's simplify this, divide through by 10, and we'll get 2x, 5y, 10z. And if we divide through by 5, we could get 16 is 2 over 5, y, and 2z. Now, this side is an integer, so this side obviously has to be an integer. And therefore, this x must be divisible by 5 in order for that to work out as an integer. So x has to be some sort of multiple of 5. So let's call it 5a. If you sub that back, you'll get 2a plus y plus 2z. Okay, so what that tells me is that since this side is even, this is already even, this is already even, this must be even. That means y must be some multiple of 2. That basically means it's even. So if I plug that in, it'll be 2a plus 2n plus 2z. Now I can further divide this and get a plus n plus z. And that basically means that I have to find integer solutions to this. So let's see, a, n, and z. Let's see what happens. Did I use z here? Yeah, well, all these different letters. Doesn't really matter what the letters are. Okay, let's see. The line that says there that at least one of each, so a has to be at least 1, I believe. Yeah, or let me think about this. Yeah, at least 1. So let's see what happens. If that's the case, then this is 1, this is 6. That's just one solution. If I stick with the 1 for a, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Okay, so that exhausts the 1s. And then you move up to 2. You get 1, 5, and then all the way to 5, 1. And then you kind of keep going like this. For 3s, it'll be 3, 1, 4, all the way till 3, 4, 1. For 2s, it will be 2, 1, 3, all the way till 2, 3, 1, I believe. Well, hold on. Let me see if I'm doing this correctly. I probably messed that up. 3. I move up to 4. That's why I messed it up. This is 4 actually. Just repeated that one. Okay, move up to 5, and then it'll be 1, 2, and then 5, 2, 1, and then finally the last one. This is ... 6, 1, 1. So I have 1 here. There's 2 here. There's going to be 3 there. So 1, 2, 3. There's going to be 4 here. This one, there's 5 of these guys, and there's 6. So the total would be 6 plus 5 plus 4 plus 3 plus 2 plus 1. And that, I believe, is 21. So 21 is the total, and that would be choice B. When the roots of the polynomial below are removed from the number line, what remains is the union of 11 disjoint open intervals. Of how many of these intervals is p positive? So let's draw the number line. And the roots looks to me like if you set this equal to 0, x minus 1, x minus 2, x minus 3, and so on all the way till x minus 10 to the power of 10. It looks to me that the roots are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the roots. 4, 3, 2, 1. Now, if they're removed, they're going to be 11 intervals. So let's see here. This is the first interval. Second, third, fourth, fifth, sixth, 7th, 8th, 9th, 10th, and then 11th is 10 onward, and this one was, I guess, anything less than 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we got those 11 intervals. And remember, these guys are all removed. So I'm going to put a little open circle to show that those guys have been removed from the number line. And they're saying, in how many of those intervals is this positive? Okay, so that means we have to kind of discuss that in detail before we start plugging in numbers. Okay, so first let me just write it out. X minus 1, x minus 2, and so on. So now let's discuss this. Anything that has a power that is even, so an exponent that is even, is always going to be positive. So for example, this guy here, no matter what you put for x, because you're squaring it, it's always going to be positive. The same story holds true for this guy, for this one, and for that one. So those ones will always be positive no matter what number you put in this whole 11 open intervals. Regardless, it'll always be positive. Those are always going to be positive. So what we really need to concentrate on is just the other stuff. So the x minus 1, the x minus 3, and the x minus 5, the x minus 7, the x minus 9. And that's it. Those are the only ones we need to concentrate on. Okay, so let's do that. And let me write on the side our intervals. And those intervals from upstairs are, the first interval is the one that's here, that one. And that's the less than 1. The next interval is I guess, I've got to look at these ones and decide what I'm going to do instead of looking at the number line, actually. So I'm going to look at this interval next. So the one that goes from 1 to 3, and then 3 to 5, and then 5 to 7, and then 7 to 9, and then greater than 9. So 1, 2, let me use a different color, actually. So 1, 2, 3, 4, 5, 6, right? Greater than 9? Yeah. Okay, from those 6, how many of these are going to be positive? All right, here we go. So if I have less than 1 and I plug it into here, so whatever, 0, this will be negative, 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 and when we multiply it all together, it'll be a negative, I believe, right? Yeah. Okay, so that is negative. If I go to the next interval, 1 to 3, so like 2, for example, this will be positive, but all the other ones will be negative. And then the end result will be positive because you're multiplying a positive times a negative times a negative times a negative times a negative. You guys understand? The next interval, 5 to 7, let's say, so 6, let's say, that will be positive. Well, hold on. Let me, before I jump the gun here, let me just see if I'm doing this the right way. This one was, I think I skipped one. Yeah, I got to do this one next. Oh, 3 to 5, so 4, let's say. If it's 4, this will be positive, this will be positive, and then this will be negative, negative, negative. And that will result in a negative. Okay, now I think I have to make sure I put this on the right line. I'm getting lower and lower. Okay, 5 to 7, if it's 6, for example, this will be positive, 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 negative, negative. 7 and 9, it'll be positive, 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 negative, and then greater than 9, positive, 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 positive. So let's summarize this. This one would be positive, this one would be negative, and this one would be positive. Okay. So now we go back to the original question. How many of those 11 are positive? Well, this interval is, this interval is, and this interval is. So let's go back and see what that means on the graph. So this was 1 to 3. So from 1 to 3, we have this interval and that interval. So those are 2 intervals for which, of the original 11. And then we have this guy, which is between 5 and 7. So 5 and 7 is this guy and this guy. So another 2 intervals. And this one is, let's see here, greater than 9. So this interval, and then the infinite interval. So we have 1, 2, 3, 4, 5, and 6. 6 intervals for which p at x is positive, and therefore the answer would be C. The answer would be C. What is the area of the region in the coordinate plane defined by the absolute value of x minus 1 absolute value plus absolute value of y minus 1 absolute value is less than or equal to 1? Okay. Well, we are going to unfortunately have to graph this. But let's first concentrate just on the first quadrant. So the first quadrant is a scenario where x is greater than 0 and y is greater than 0. If that is applied to that, it reduces to x minus 1 absolute value plus y minus 1 absolute value, and I think that it'll be less than or equal to 1. That doesn't change. Okay, so now how do I graph this? All right, so I guess I'll just do it in the very basic way, just plot some points. Let me just stick to the basics here. Integers, when it's 0, it will be 1, and therefore this is going to have to be 1, right? Oh, but the fact is that it's less than. Well, less than or equal to, and I'm just doing equal to. Yeah, because what I'm doing is just this guy here. I'm doing this one, because when x is 0, it would be 1. And then y, hold on, I forgot another. Y would have to go. Let's just do the equal, and then I guess it'll be in a range. So let me just do it and plot it. This will be 1 and 0, 1 and 2, and then 2 and 1. Those are sort of the boundaries, I think. So let me plot this now. So we have 0, 1, 1, 0, 1, 2, so up here, and then 2, 1. So these are the boundaries. So if you connect them, that will sort of be the range in which this holds true. Okay. All right, that's very good, I think. And then therefore we have to do that for the other 4 quadrants. The other 4 quadrants are x greater than 0, y less than 0. Then the other one would be x less than 0, y greater than 0, and then of course both of them less than 0. And when you do that, and I'll let you do that, it'll be exactly the same in terms of the shape. Very similar, it's just in a different quadrant. And what they want, I believe, is the total area. Okay, well, since they're exactly the same, we'll just calculate the area of that one and then multiply by 4. Well, this was, from here to here was 1, right? And from here to here was 1. So using Pythagoras, you can easily figure out that that's root 2. And therefore, this is all root 2. So that means that's a square with side root 2. So its area would be root 2 times root 2. So that looks like 4 times 2, which is 8. And therefore, B is the answer to that question. How many ordered pairs of integers mn satisfy the equation m squared plus mn plus n squared is equal to m squared times n squared? Let's put everything on one side and let's see what we can do with this equation. Let's put it into a form that makes it look like a quadratic. So 1 minus m squared plus m times n plus m squared. And this is of the form ax squared plus bx plus c is equal to 0. And you guys remember the quadratic equation, x would be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a And what's under the radical, that b squared minus 4ac, is known as the discriminant. Discriminant. You guys remember that. Okay, now they want integer solutions, so that means that m and n both have to be integers. And the only way in this equation that m and n will be integers is if the solution has a discriminant that is a perfect square. Because otherwise, if it didn't, it would be a radical, and it would be a, or there would be a root in the equation. So we need the discriminant to be a perfect square, I think. Yes. So what is the discriminant, first of all, on this guy, this b squared minus 4ac? It looks to me like it will be m squared minus 4 times 1 minus m squared times m squared, I believe. So it's going to be m squared minus 4m squared plus 4m to the power of 4. And that has to be some perfect square. So whatever, let's just call it k squared. All right, let's see what I can do here. First, let me just collect like terms. And factor out an m squared. 4m squared minus 3, I think. 4m squared, yeah, k squared. Okay. So, the discriminant can be a perfect square, or it could be 0. If it's 0, that will also help, because that will make the discriminant vanish. Well, that's easy. That happens when m is 0. Okay? If it's a perfect square, this is already a perfect square, so this has to be a perfect square. Has to be some, whatever, t squared. And let's see here. That happens when m is equal to 1 and when m is equal to minus 1. Okay, so I think I got it. So now I just have to go back and figure out my values for n. And how do I do that? Where do I go to figure out n? I guess the original equation, I guess? Yeah, just the original equation. Okay, so let's remind myself, what is the original equation? It's m squared plus mn plus n squared is equal to m squared n squared. When m is 0, n will be 0. So that first mn is 0, 0. When m is equal to 1, well, I'll let you sub it in and solve for n. N will be negative 1. So this will be 1, negative 1. And then when m is, what's the next one here? Negative 1, n will be 1. So this will be negative 1, 1. So we got 3 of these guys, 3 solutions, and therefore the original question's answer is C. What is the least positive integer, m, such that m times 2 factorial times 3 factorial all the way to 16 factorial is a perfect square? Let us write these all out. Well, I don't think I need to write them all out initially. Okay, so if I have this, the m is going to be all alone for now, and if I add them all up, you get a 2 from every one of them. So since there's 15, you'll get 2 to the power of 15. 3 from every one of them except the 2 factorial. So you have 14 of those guys. 4 from every one of them except the 2 factorial and the 3 factorial. So you get 4 to the power of 13, and then so on. You guys get the point. And this I will write out in its entirety. Say 10, 8, 9, 10, 8, 11, 7. 12, 6, 13, 5, 14, 4. Let's see if I can fit this in here. 15, 3, 6. I probably missed one here. What did I miss here? 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. I believe that is accurate. Okay, now what we need to do is analyze this one step at a time. We want this to be a perfect square. Now, forget about m for now. We'll concentrate on m later. How many of these are perfect squares? Well, if a perfect square is when the exponent is even. If the exponent is even, it's already a perfect square. So these guys are already perfect squares. So we can just get rid of them because we don't need to concentrate on them. Okay, so now what we're left with, that's what we need to concentrate on. Okay, so I've got to combine them though. So this 2 to the power of 15 is already in its basic factorization. But the other ones, I have to make them. The 4 to the power of 13 is really 2 to the power of 2 to the 13, so that would be 2 to the power of 26. The 6 is going to break that up, 2 to the power 11, 3 to the power 11. The 8 is 2 to the power 3 to the power of 9, so that would be 2 to the power of 27. This is 2 to the power of 7, 5 to the power of 7. That is 2 to the power of 2 times 3, right? So that's going to be 2 to the power of 10, and then 3 to the power of 5. This is 2 times 7, all to the power of 3. So that's going to be 2 to the power of 3, 7 to the power of 3, and then finally that's 2 to the power of 4, correct? So now let's go back and revisit this again. How many are perfect squares? That's a perfect square. That's a perfect square. Again, same kind of story, right? You're just getting rid of anything that's an even because that's already a perfect square. Okay, I think I'm exhausted that. I think. Okay, so let's go back to the drawing board and see what we have. We have the m, and then we got to combine the 2's. So 15 and 11 is 26. Plus 27 is 53. 60. And then 63. 63. Okay. Or whatever. 3, 11 and 3, 5. So that's 3 to the power of 16. 5 is just 5 to the power of 7. And then the 7 is just 7 to the power of 3. Okay, we're coming down to the nitty gritty. That's already a perfect square. And I think this is it. This is the farthest I can go. So in order for this to be a perfect square, we have to now turn our attention to the m. The m has to make these guys have even exponents. And that is possible if the m has just one power of 2, one power of 5, and one power of 7. Because they want the least. I'm sure there's many, many infinite numbers that would make that a perfect square. But the least would be, at bare minimum, we need one power of 2, one power of 5, one power of 7. And therefore, that looks to me like 70. So the answer would be C. Define an up number to be a positive integer of 2 or more digits where the digits are strictly increasing, moving left to right. Similarly, define a down number to be a positive integer of 2 or more digits where the digits are strictly decreasing, moving left to right. For instance, the number 258 is an up number and 8620 is a down number. Let U be the total number of up numbers and D equal the total number of down numbers. What is U minus D absolute value? Up number. Let me give an example of an up number. So it's increasing, right? So like 1, 2, 3, 4, and so on. 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the largest. Well, yeah. Yeah, that's the longest you can make because these have to be digits. You can't put a 10 there because that 10 is not a digit. And for down number, the same kind of story, but this time it's got to be decreasing. So 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Okay, so that's the absolute biggest. Now, if, I'm trying to think, like this answer, it can't possibly be 0 because it's just too easy because AMC is not going to be that easy, especially by the time you get up to problem 16. But that's very tempting for me to choose because it seems like every up number has a matching down number, right? Because this is a perfect example. So the total number of up numbers should be equal to the total number of down numbers. So u should be equal to d, and therefore u minus d would be 0. But instinct tells me that that can't possibly be correct. So let's see, what is the story here? I think it has something to do with a mismatch. And I think this is a nice little clue they give us, which is very nice of them. 8620. If I were to do its matching, this is a down number, right? Yeah, I even tell you that. So if I were to do a matching up number, it would be 0268. But let me read this question again. Define an up number to be a positive integer of 2 or more digits where the digits are strictly increasing. Define a down number to be a positive integer of 2 or more digits where the digits are strictly decreasing. Okay. But these are not matching. The reason is because this is no longer the same number of digits. This is a 4-digit number, and this is a 3-digit number, right? Because the 0 in the front makes this a 268. And 268 would actually have a matching 862. So these are matching, but this is not matching with this. So that means that anything that has a 0 at the end will not have a matching up number. I got it. So that's why u and d are not equal. Okay. So now I have to figure out how many of those numbers have a 0 at the end. Well, the maximum it could be is 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want a 0 at the end. And then we got to count how many of those. Yeah. Okay, well, for each of these, we are going to either have it or not. Like there's going to be a number there or no. So there's two possibilities. Either you have a number there or you don't have a number there. Like let me write it out first. Like this is the absolute longest. Well, actually, I need one more. Yeah, how many? That's 10. Ooh. Okay, well, whatever. We want the 0 at the end. So for each of these, we're going to include it or not. And therefore, there's going to be two possibilities for each of these. 2, 2, 2, like this. So the total would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2 to the power of 9 is the total number of numbers that have a 0 at the end. So 512 is the extra. So for example, if whatever D is, hold on, which one is more, U or D? This is a down number, right? So there's going to be more down numbers. So if U down, yeah, there's going to be more down numbers. So it's D is equal to U plus 512. Is that right? Because there's more, yeah, there's more down numbers. So 5, if you subtracted them, U minus D, and take the absolute value, would be 512. And 512 is one of the answers. But here's the thing. This is a very tricky question, actually, because one of these 512s is a scenario where you did not have any of these numbers. You didn't include any of them. And that is complete 0. And complete 0 does not satisfy the condition of having 2 or more digits. So that cannot be included. Does everything else satisfy? If I have a 1, 0, that's 2 digits. So we actually have to subtract that scenario where everything's 0 and it's 511. So this is actually 511 and this would be 511. Okay, so after that much thought, the answer is E. A rectangular box P has distinct edge lengths ABC. The sum of the lengths of all 12 edges is 13. Sum of the areas of the 6 faces is 11/2, and the volume is a half. What is the length of the longest interior diagonal connecting the two vertices. So this is a box, right? So let me, and this is not going to be drawn to scale by any means, but I just want to draw it. If I know how to draw a box. Okay, I think that's a box, right? All right. So A, B, C, whatever. This is A, this is B, this is C. Okay. Now let's talk about what they tell me. The sum of the lengths of the 12 edges. So that means that's going to be 4A plus 4B plus 4C. Just interpreting the sentences into a formula, into an equation. Sum of the areas of the 6 faces is 11 over 2. So that basically means 2BC plus 2AC plus 2AB is 11 over 2. And the area, or volume rather, is a half. So A, B, C, A times B times C is a half. And what do they want? The length of the longest interior diagonal. And then the length of the longest interior diagonal is where? I think it's from... I think it would be from, let me think about this for a second. Where, from here to here, perhaps? From that corner to that corner? That's the longest, right? Yeah. And then how would you figure that out? I think using double Pythagoras. So first you'd have to use Pythagorean theorem to figure that out. Okay, I got it. Yeah. So the diagonal, let's just call it D, and let's call this small d. And then, so first and foremost, this is C, right? So the small d would be B squared plus C squared, right? Well, the square root of that, using Pythagoras. And therefore the big D would be A squared plus D squared. And therefore D squared would be A squared plus B squared plus C squared. And therefore D would be the square root of that whole thing. A squared plus B squared plus C squared. Okay. And then now I have to use these guys to try to figure out what is that. Okay. I think I can do that. Well, we know that A squared plus B squared plus C squared using simple algebra is the equivalent of A plus B plus C all squared minus 2 times AB plus AC plus BC. And that's just, you can expand this and subtract that and get this to verify. It's very standard. So a lot of these we've already been given. This one gives me A plus B plus C. It'll just be 13 over 4. And then the 2A, that's this over here. That's going to be just 11. Hold on here. That's just 11 over 2, right? I think you just put it in like that. Okay, let me just see what this is 169 over 16. And then, therefore, if I do the common denominator, we're going to multiply top and bottom by 8. So 88 over 16. And that's going to be 81 over 16. And therefore, if I take the square root of that, because I want the square root, because I want A squared plus B squared plus C squared square root, that's going to be the square root of 81 over 16. And that is 9 over 4. And I believe 9 over 4 is one of the answer choices. It's D. Suppose A, B, and C are positive integers such that A over 14 and B over 15 equals C over 210. Which of the following statements are necessarily true? Before we jump right into this, let me do a very quick summary of what is GCD for those of you who may not remember. GCD, greatest common divisor. So the best thing to do is to, if you have two numbers, let's just make up two numbers. So 14, let's just use 14 and 15, why not? the very first thing to do is to break them up into their prime factors. So this would be 2 to the power of 1, 7 to the power of 1. This is 3 to the power of 1, 5 to the power of 1. And then for greatest common divisor, you think smallest. I know that's counterintuitive, but that's how it's done. And let me explain what I mean by that. You look at the smallest power of each prime number. So for example, if I were to say, what is this? Well, for the first prime number that we are in discussion, that's included, it's 2, right? What's the smallest power of that? Where here it's 1, but here there's nothing. There's no 2. It's 2 to the power 0. So the smallest power of 2 is actually 0. If you look at both of those. If you look at this guy, and then if you look at the next guy. Similarly for 3. The smallest power is also 0 because there's no 3 in there. Smallest power of 5 is 0 and smallest power of 7 is 0. So this actually is 1. Now let's do one where you won't get 1. So let's try 2 to the power of 1, 7 to the power of 1, 11 to the power of 2, 11 to the power of 1, 13 to the power of 2, like that. Okay, same kind of story. Think smallest. For 2, it'll be 0. For 7, it'll be 0. For 11, it'll be 1 this time. For 13, it'll be 0. So this is 11. So I just wanted to do that crash course to kind of familiarize you with what is GCD. All right, so let's go to the question now. We want to see which one of these 3 is true. Okay, no problem. Let's see. Let's start with the first one. If we can prove that it's false, then we can just get rid of it. So let's see if there's a counter example. And I quickly can see that if I use A equals 3 and B equals 5, I can get a counter example. First, let me simplify this. This simplified would be 15A plus 14B is equal to C. So if A is 3 and B is 5, C would be 15 times 3 plus 14 times 5, which is 45, plus 70, which is 115. So therefore, if you look at 1, GCD of A14 would be the GCD of 314, and that's the GCD of 3 and 2 times 7, and that is equal to 1. So that part is so far true. Let's try GCD of B15. That is the GCD of 5 and 15, and that is the GCD of 5 and 3 times 5, so that's going to be 5, correct? So that obviously is not equal to 1, but they're saying or, so we're still kind of valid. We just said, okay, that one's true so far. Yeah. Okay, so now let's see if this holds true. The last one, which is GCD of C210. That would be the GCD of C, which I calculated to be 115 and 210. So if I break it up into prime factors, what's that? 5 times something. 5 times 8. Wait, hold on. It would be 5 times, let's see, 23. Yeah, 5 times 23. And then 210 is 2 times 3 times 5 times 7. So this GCD is 5, which is not equal to 1. So it's not equal to 1. So this is false. So that's false. So that means we can look at the answer choices and eliminate. We can eliminate A, we can eliminate B, and we can eliminate C, because they're saying which of the following is true. So now we're just down to D and E. Okay. So we're down to just D and E. So I guess we now concentrate on the second guy, which is if the GCD of C210 is 1, then the GCD of A14 is 1, or the GCD of B115 is 1. Okay. Well, let's see. If I do that, if the GCD of C210 is 1. Well, we're no longer using this anymore. This has already been done. We're just going to use something else. If the GCD is 1, that means that the C cannot have any of the same prime factors as 210. So what was 210 again? It was 2 times 3 times 5 times 7, right? So C cannot have any of those prime factors. So let's just say it's something else. It's 11 times 13. Because it cannot have 2 or 3 or 5 or 7. Because if it did, the GCD would not be 1. Okay, that takes care of the first part of part 2. But now we got to concentrate on this. So, since, where is that equation? Way up here. Yeah, that's still valid because that's valid, right? 15a plus 14b is C. So 15a plus 14b is C. That's still valid. So what did I do? I set C to be 11 times 13, right? Because I can't have any of these prime factors. So C is whatever. 11 times 13 is what? 143? Okay, so I've got to find an A and B that make that 143, and I think 3 and 7 would do it. So 45 plus 98, yeah, 3 and 7. So that means my A is 3 and my B is 7. So let's see. The second part of this, GCD of that and GCD of this. Okay, let's see if that holds true. GCD of A14, which would be GCD of 3 times 2 times 7, that is indeed 1. And then the next one, GCD of B15, is it B15? Just double, yeah, it is B15. That's going to be GCD of 7 times 3 times 5, and that is also 1. So there you go. This checks out. So that means B is true. B is true. So as B is true, then 2 is true. Therefore, it's answer choice E, because this is stating that 3 only, that they're basically saying that 2 is false in choice D, so it's choice E. Sonia the frog chooses a point uniformly at random lying within the square 06 times 06 in the coordinate plane and hops to that point. She then randomly chooses a distance uniformly at random from 0, 1 and a direction uniformly at random from north, south, east, west. All of her answer choices are independent. She now hops the distance in the chosen direction. What is the probability that she lands outside the square? Let's make a coordinate grid and see what we can do here. So it's a 6 by 6, right? So it's like this. And each jump is anywhere distance 0 to 1. So maximum distance is 1. So if she is 1 away from the square's boundaries, she won't be able to hop outside of it. So let me draw that. Let me just see if I can try to attempt to draw this to scale. 1, 2, 3. So 1, 2, 3, 4, 5. Okay. So that's 3, 2, 1, 2, 1. Okay. Not perfect, but it's okay. All right. So let me just see. Okay. So if she's in that box, like for example, she's here, there's no way she's going to hop outside because the maximum she can hop is 1 according to that distance. So let's just say, well, yeah, okay, that's fine. So then where do we go from there? Then I have to look at other regions. Yeah. So let's label this. This is in the center. I don't really care because there's no way that she can go out of this square if she's in the center. But if she's in region 1, which is the corners, or region 2, there is a chance for her to get out of that square. So that's what we need to discuss. So probability of being there, of of being in of being there in that region. So this is region, hold on, let me make sure I write this properly. So the region 2 and region 3. And then we're going to talk about the probability of going outside the box, or going outside the square. Yeah. Okay. So let's see what we can do here. So first of all, the probability of being there is just going to be the areas, right? So that is a 1 by 1 square, I believe. So that the total area is 4 of those 4 regions. Hold on, what, am I doing this right here? Sorry, that's region 1. And there is no region 3. This is region 2. I don't know why I put that in there. Okay, so the probability of being in region 1, sorry about that, is 4, because those are 1 by 1 boxes, and the total area would be 6 by 6 of the entire square, so 36. So that's 1 over 9. And then in a similar way, that's a 1 by 4, correct? And there's 4 of them, so 16 is the total area. And again, the total area of the entire square is 36, so that looks like 16 over 36, 8 over 18, 4 over 9. Okay. So that's fairly straightforward. Now this guy here, this is what we have to concentrate on, probability of going outside. So for region 1, well, the directions is something we need to talk about. You're going to go outside if you're going up. Well, in this guy, first of all, this first box here, if you go up or if you go west. Yeah. So you got, of the 4 directions, you got only two choices. Either you're going, there's 4 directions, north, south, east, west, but you can only go outside of the box if you go north or west. And the chance of a distance from 0 to 1 is a half. So to choose a distance to go out, that probability is a half. Then you multiply these two, and when you do, you get a quarter. And then to get the total probability, you'd have to multiply those two guys. So that'd be 1/9 times a quarter, which is 1 over 36. And then same kind of story here for this guy, which is region 2, so it would be this region. Any of those guys. You can only go outside of the box if you go east. If you go north, it would be impossible because you'd have to jump more than 1, and that's not allowed. If you go south, it'd be impossible, and obviously going west, you won't be able to go outside of the box with a maximum jump of 1 unit. So of the 4 directions, north, south, east, west, you can only choose 1 direction. And then the probability of going outside the box, is equal to choosing a distance to go out between 0 and 1, and that would be a half. So you multiply those two, and you get 1 over 8. So the total probability would be that times a half, would be 4 times 9 times 1 over 8, which is 4 over 72, which I believe 1 over 18 in lowest terms. So you add these two to get for the both regions. So it'll be 1 over 36 plus 1 over 18, and that is going to be, let's see, 2, so 3 over 36, which is 1 over 12. And 1 over 12 is answer choice B. 4 congruent semicircles are drawn on the surface of a sphere with radius 2 as shown, creating a closed curve that divides the surface into 2 congruent regions. The length of the curve is pi times root n. What is n? So they have drawn this in nicely, and this is a curve. And then this kind of goes straight, and you can barely see it, but it kind of curves around like that. And similarly, it kind of curves around like this, and then it goes back into a curve. So if you flatten it all out, it would be kind of like this. So you got these 2 curves, kind of like a track, right? A running track. But here's the thing. Let me see if I can draw this in a way that you can understand. This part, that curve, it kind of represents this part, okay? Now, let me use a different color. Now you're going straight here, correct? And that's this part here. But that part is actually the equivalent of this. If you flatten it all out. See, right now it doesn't look like that, but that's because it's curved on a sphere. But if you were to take it out and put it flat on a table, it would look like this. So this is pretty obvious that that blue section is a semicircle. Semicircle. But this part is also a semicircle. It's just a semicircle that's been flattened out. So really what you have is 4 semicircles. The blue, the green, and then I guess this would be another one. And then, of course, the other semicircle, that's pretty obvious. So the 3D conceptualization of this is actually very challenging. And I'll admit, I'm not very good at those things. But when I looked at this diagram very carefully, or what you can do is if you're in practice, obviously not on an exam, but in practice, just take like a tennis ball and draw it. And then you'll be a little bit more obvious. You can turn it around. You can flip it around. On the math contest, you can't do that. But if you did it on a tennis ball, you probably could. Okay, so what are they asking for? They're asking for the length. So I guess they're saying what is sort of the diameter or the perimeter, I guess is a better word to use. Okay. So the circumference of a circle is pi times diameter, right? Or pi times 2 times the radius. So this looks to me like 2 circles because it's 4 semicircles. So really what we're looking for is 2 of these guys. So 2 times pi times 2r. So 4 pi r. Yeah, I believe that's right. 4 pi r. Now we just have to figure out r. Okay, I got it. Okay, so how do I figure out r? Okay. Now, before I figure out r, I have to first define what is r. R is not the radius of the sphere. R is the radius of this semicircle. So that guy right there. So let me attempt to draw that in there without. Hopefully, it won't make the diagram too messy. So that. You see that is the diameter of that semicircle. Does that make sense? It's basically the same as this here. Let me just draw it again. It's the same as this right there, what I just drew. So what I just drew is 2r. And then that means like if I drew that kind of a line anywhere, like if I drew it in the center, it's the same. So let me see if I can do that again. Like for example, if I do it here, that's the same. Now what I'm going to do is attempt to draw a line from the center of the sphere to the edges of that red line. And let me just put it in first, and then hopefully it'll make sense once I explain it. So like this. That way and this way. And then now what I'm going to do is I'm going to put it sort of in a non-3D image. So let me just put it like this. So what I've done is I've taken this red line that's there, and I've taken the center of the sphere. This circle sort of represents a cross section of the sphere. I've drawn these two lines like that. And then I can draw one other line from here to here. Okay, now let's explain this. Label this from the center of the sphere to the perimeter, I guess, of to the edge of the sphere, obviously, is the radius of the sphere. So that's 2. That's 2. And then the red part, that is the diameter, so I can break that up into two radii. So this is R and this is R. And now we have the tricky part is, what is this here? That one is the hardest to conceptualize. And the way I did it, let's see if I can even attempt to try to explain it. The distance from that to that is the same as the distance from, let me draw two lines here. Hopefully this won't be too confusing. But this, I'm going to connect this guy, right? So the distance from here to here, here to here, is the same as the distance from here to there. Now let's talk about this. Let's discuss this very carefully here. Here to here is from the absolute center of the sphere to the midpoint of that line right there. Now that, I don't know what that is, but I'm comparing it that if you were to just come out to here and then come out to here, it would be the exact same. So we can conclude that this is also R right here. And if that's the case, and since I've drawn that in a right angle, R squared plus R squared is equal to 2. So 2R squared is equal to 2. Hold on, 2 squared I should have said. And therefore R squared is equal to 2, and then R is equal to root 2. So root 2 is what we'll plug in here. So 4 pi root 2. So pi, that's what, put it in the radical, will be 16 times 2 root 32. And they're saying that is equal to pi root n. So therefore the n is equal to 32. And therefore number 20 would be A.